office, and I actually lead on our engagement with the aviation industry, including leading the space weather work stream within the ICAO framework. So I'm a relationship manager at the moment, but my background was in operations. I used to be a weather forecaster and a space weather forecaster too. So I've got that sort of understanding of the operational side of things as well. So what I'd like to do today is give you an introduction to space weather. I'm going to assume no prior knowledge really of what we mean when we talk about space weather. So I'm going to cover what it is, what the impacts are, so why it matters, how we forecast it at the Met Office. And I'd also like to touch on some of the new developments which we've got and how we're planning on making our forecasts more sort of user-friendly and impact-based in the future. So I will start with the simple question of what is space weather? Well, electromagnetic radiation, energetic charged particles, and charged plasma from the sun can interact with the Earth's magnetic field and upper atmosphere. And it's these disturbances which we know as space weather. So there are different types of space weather. Space weather is essentially a catch-all term for activity on the sun, which impacts us here on Earth. There is also a background level of constant radiation known as galactic cosmic radiation, which is mentioned there as well. But by and large, when we're forecasting, it is the activity on the sun which has got the biggest impact on us here on Earth. So that's what we're focusing on. So different types of space weather takes a different amount of time to arrive at Earth after occurring on the sun, and they can have different impacts. So I'll go through them quickly here and then go into the impacts in some coming slides. So first up, we've got solar flares. These are bursts of electromagnetic radiation. And we see these in satellite imagery in certain wavelengths. It's these bright flashes of light on the sun. And these are traveling at the speed of light. So after occurring on the sun, they arrive at Earth within about 8-9 minutes. So the impacts are being felt as soon as we see them occur. In terms of the impacts, solar flares interact with the layer of the Earth's atmosphere, the ionosphere, which is pretty critical for some communication systems. So when we're using HF comms, it reflects off the ionosphere. If we have solar flares, it disrupts that layer, which means that it can impact on HF comms. It can also, to slightly lesser effect, impact on satellite communications and GNSS signals, as those signals are traveling between satellite and receivers. So those are solar flares. Next up, we have solar radiation storms. These can occur at the same time as solar flares, but not always. They're pretty difficult to forecast because they are high energy particles, predominantly protons. They travel slower than solar flares. So typically we can see the impacts in minutes to hours after a solar flare occurs. We'd be looking for signs of a solar radiation storm on Earth. Now, much of the radiation from the sun is blocked out by the Earth's atmosphere. So a lot of the time when we see a solar radiation storm, it's impacting the Earth's outer radiation belts, so where satellites orbit. I've actually got some slides about that sort of later on in this presentation. When we're interested in terms of aviation, it's when we get particularly energetic solar radiation storm, and the energy of the particles means that it can pierce through the layers of the Earth's atmosphere, and we could get what's known as a ground level enhancement, which is an increase of radiation at flight altitudes and down to the Earth's surface. As these are charged particles, typically it affects polar regions more than it would equatorial. So the higher altitudes, higher latitudes, flights would be most impacted by solar radiation storms. And then finally, we've got geomagnetic storms, which are caused by coronal mass ejections from the sun. And these are eruptions of charged plasma, charged matter from the sun. These can occur at the same time as solar flares. So our forecasters will be looking for a solar flare and then looking for the sign of a CME, a coronal mass ejection, following on behind. These are billions of tons of charged particles which will be thrown into space. And if directed towards the Earth, when it arrives, it interacts with the Earth's magnetic field, upper atmosphere, and the energy can in fact be transferred all the way down to the Earth's surface, causing what is known as a geomagnetically induced current. When we see these set up along the Earth's surface, typically electric charges take the path of least resistance, which can be driven by underlying geology, proximity to coasts and so on, but also through long conductors is the best way to get an electric field moving from one place to the other. So there's the potential for impacts on things like pipelines, the railway grid, the railway network, and power grids in extreme cases. So geomagnetic storms are the most impactful type of space weather. It can cause disruptions to communication systems by altering that layer of the atmosphere, the ionosphere that we spoke about before, which can block GNSS signals and satellite communication signals as well. It can then lead to this extra risk, which I just mentioned, the geomagnetically induced currents. Introducing currents to transformers can disrupt the power grids across the UK and indeed globally. So geomagnetic storms following on from CMEs, we fortunately have a degree of forecast skill for these. They're still travelling incredibly fast. The background solar wind, for reference, is generally about 300 kilometres per second. CMEs, coronal mass ejections, can be travelling several thousand kilometres per second. With the sun being 140 million kilometres away, we're still looking at a heads up between about 15 hours and several days when we see one of these storms leave the sun before it arrives on Earth. That means we've got a degree of forecasting skill. Our forecasters can look at the sun in satellite images, such as the ones shown here, and get an indication as to whether that storm is coming towards Earth. And if so, we have modelling tools which we can then use to give an indication of the arrival time at Earth. So geomagnetic storms can be very impactful. They can have a lot of negative impacts when it arrives on Earth. They are also responsible for the aurora. And I always like to say, like, I'm from the north of Scotland, so up there you should typically see the aurora pretty frequently. I currently live in the south of England, so when I see it now, I know that I'm going to be pretty busy at work. The stronger a geomagnetic storm, the further south the impacts are felt. So space weather then has a range of impacts from those different types of space weather, from the flares, from the solar radiation storms, from the coronal mass ejections leading to geomagnetic storms. And it's impacting a range of different systems, whether that's satellite communications, GNSS, things you're using for communication, navigation, right the way down to the risks from radiation. So the neutrons that you can get from radiation can impact electronic systems and avionics and cause single event effects, as well as having that increased biological dose of radiation across high altitudes and high latitude flights. And then in the most significant events, we can see these induced currents in long conductors, which can lead to damage to the power grid. So we have these different impacts. They arrive at different times after occurring on the sun, and they can last for a different length of time once it happens on Earth. Now, we have been seeing an increase in space weather activity over the last couple of years, and this is to be expected. The sun has got a solar cycle of 11 years, and this goes from solar minimum, which is when we see the fewest sunspots on the sun, to solar maximum, where we have the most number of sunspots, and back down to solar minimum. So from solar minimum through solar max back to solar min is roughly 11 years. Space weather, solar flares, coronal mass ejections, radiation storms, they typically originate from these sunspot regions on the sun. These are areas where we have a tightly bound magnetic field, a lot of energy tied up, which means that when we have more sunspots, typically you see an increased frequency in the number of space weather events. And it looks like we hit solar maximum sometime in 2024. You don't really know until you're on the decline to solar minimum that you have reached solar maximum, such as the way that it works. It can fluctuate, as you can kind of see from this chart, it can fluctuate month to month. So you need to be sure that you're well out of solar maximum before you can declare that it has occurred. But just because we're not at solar maximum anymore, it doesn't mean that we're out of the woods in terms of significant space weather. Whilst that number of sunspots can dictate the frequency of severe space weather, it's not necessarily a guarantee that we're going to see the most impactful types of space weather. In fact, traditionally, looking historically, the most impactful space weather has actually occurred on the downturn from solar maximum towards solar minimum, which is where we are just now. So it's safe to say for the next couple of years, we're on heightened alert for significant space weather events. Also worth saying that the previous solar cycle, which ended in 2019, was surprisingly quiet. There were some large space weather events, but they didn't arrive at Earth. So we were quite lucky in some respects that we missed the largest solar storms. And if you think about the technological advances that there's been in the last 20 years, since we last saw some significant space weather events, we are more impacted by the space weather that we see now than we were 20 to 30 years ago. So to put some things in context, when it comes to historical events and impacts, if we go back now to 1859, there was the largest space weather event which was recorded by humans, known as the Carrington event, named after the astronomer Richard Carrington. And he was monitoring the sun and monitoring sunspots. And back in 1859, so enormous solar flare occurring on the sun, and then linked it to effects which were being felt on Earth. So back then, the technology at the time was heavily impacted. Telegraph lines across Europe and the US were seen to spark and equipment was catching fire. The lines were continuing to transmit information even though no energy was being applied to them. And there are reports that the aurora was being seen as far south as the south of Europe and the Caribbean. So that is what we use as sort of a reasonable worst case scenario, a return event of 1 in every 100 to 150 years. We're looking at an event on the scale of a Carrington type event. Since then, we haven't had an event quite so strong, but we have had some other significant events of note. There were geomagnetic storms in 1989, which particularly impacted North America, and Quebec in Canada lost power. So 6 million people lost power for 9 hours when safety systems tripped out and plunged a blackout across there. And then in 2003, Malmö in Sweden had a complete power blackout. And at the time, 47 satellites experienced temporary outages. And as I say, there's been an enormous technological advance in the last 20 years or so. So 47 satellites back in 2003 was roughly 5 to 10% of the satellite fleet. Now I think we've got something between 20 and 30,000 satellites in space. So when you start to get your impacts now, you're seeing this real sort of significant increase in impacts. And then back in 2024 in May, we had a reasonable space weather event. It was ranked as sort of G5 on a scale of 1 to 5. A space weather event. It was the first G5 that we'd seen in about 20 years. And although it was nothing on the scale of a Carrington event, we did start to see those impacts, particularly to technologies. So we know that power companies in North America and New Zealand were seeing these currents through their transformers, so start to put in place some mitigative actions. We also had reports of impacts to HF comms, GNSS systems, including GPS, and we know that numerous satellite operators had to make a lot more corrections to their orbital plans. So yeah, this kind of puts things into perspective. The Carrington event we consider a sort of 1 in 100, 150 year event. The May event of 2024 was a reasonable size event, but does not compare to what's a reasonable worst case scenario for the UK could be. So in terms of what a reasonable worst case scenario for the UK would be, it is because of these impacts to technology, to our infrastructure, that space weather is recognised on the UK government's National Risk Register, using a sort of return of a Carrington type event as a sort of an example of what we might see. And it has been on the risk register since around about 2011, and in 2023 it was actually elevated level of impact, so it is now recognised as one of the significant risks to the UK. If we were to get an interval of severe space weather, it's estimated it would be in the order of 2 weeks. It is incredibly difficult to predict the exact order, size, and duration of individual space weather phenomena. So from a forecasting perspective, we can look and we can see that there are sunspots of concern, sunspots that we know have got a lot of that energy tied up in them. So there's that potential that we could see solar flares, see radiation storms, and see coronal mass ejections. But the science isn't there that when we see this, we can actually predict that exact order and magnitude of the events before they happen. As I sort of show, different systems, different technologies can experience the impact simultaneously, sequentially, or unpredictably, so effectively randomly. And it's highly likely that system failures will interact with each other, cause cascading failure modes that are fundamentally difficult to predict. Excuse me. So whilst we are fairly up to speed with what the impacts could be, ahead of time it's incredibly difficult to tell exactly what a severe space weather event would be as it's happening. Excuse me 1 second, I just need to take a drink of water. So it is for these reasons, for these risks of space weather, that the Met Office has been delegated the ownership of the severe space weather risk on the National Security Risk Assessment or National Risk Register. And back in 2014, the Met Office Space Weather Operations Centre, or MOSWOC, went operational as a 24/7 staffed operations, forecasting, predicting space weather. We are located within the Operations Centre at Met Office. Generally, our space weather forecasters are meteorologists who we train in space weather. We're one of very few global guidance centres forecasting for space weather. Our partners in the US, the Space Weather Prediction Centre, are the other main global guidance centre, and there's coordination between us and the US. We're a national capability and we support a range of different sectors, whether that's from government, critical national infrastructure, defence, and the public. So our forecasters are constantly monitoring the sun, looking for signs of activity to give an indication that we could expect severe space weather. Then when we see it, we'll be trying to produce forecasts to help those different sectors mitigate against the worst of the impacts. So I'll show some of the forecasts that we have at the moment. We produce twice a day a space weather bulletin. It gives a summary of space weather that we've seen over the previous 24 hours. And a forecast out for the next 4 days, given the potential for geomagnetic storms, solar flares, and radiation storms. We have two versions of these. We've got a plain language one, which is available on our public website and designed for sectors which are impacted by space weather, but don't necessarily have a deep space weather background. And we have a technical version, which is more suited for users who have got a more scientific understanding of the background of space weather. We also give forecasts giving the risk of geomagnetic activity for the next 24 hours and out to 3 days. And then when we start to see space weather activity, we've got a range of alerts, warnings, and watches for the different types of space weather to give an indication of the magnitude. During the most significant space weather events as well, we'll have additional briefs, which we'll send out to government departments, critical national infrastructure providers, and so on, to give a heads up that we're expecting something more significant as well. Now, I touched on radiation and sort of some advances, mentioned we have some advances in space weather forecasting, which we've been bringing into the Met Office. And we've also recognised where there's some capability gaps in our forecasting. And there's a lot of work that we're doing just now to increase our ability to forecast and monitor and provide more impact-based advice for different sectors. And an example of this was in November last year when we had a ground level enhancement. So this is where the radiation is able to penetrate down to the Earth's surface. As I mentioned before, generally the Earth's atmosphere filters out much of the radiation, but in this case we saw an increase in high energy particles following a solar flare, and this penetrated all the way down to ground levels. So what we're showing here is on the top right, I'll start there, that is a trace of the weather satellite with space weather monitoring equipment on it. The different colours of traces are different energy levels of protons. So in this case, what's interesting is the orange, which is the lowest down, that is high energy protons, and you can see that there is a slight increase in that during this time. And that's the most significant because those high energy particles had an increase. It meant that the radiation levels increased further down through the atmosphere. Now, one thing which we've recently started to do at Met Office is launch radiation monitors on radiosondes. So on the left-hand side there's a picture which our colleagues from the University of Surrey took when we were doing a test launch of one of these radiosondes back in October. Actually, it's very well timed. And these radiosondes can be launched from our weather observing sites in Lerwick up in Shetland, Camborne down in Cornwall, on demand. So when we saw this increase in radiation in those sort of higher energy bands, we launched these balloons into the radiation storm, which is pretty much a new capability that nobody's really done before. And then what we can see is the trace on the bottom there, on the bottom left, shows that there was an increase in radiation up through the atmosphere. And this was what was recorded from Lerwick and Camborne during the solar radiation event. And it gave us like never seen before understanding of what happens with radiation through the atmosphere as we have one of these radiation storms. And then on the right-hand side there was also a ground-based neutron monitor, which we've recently had installed. This one up in Lerwick again, one down in Camborne. And in this case, it captured the enhancement of radiation at ground level. The spike there is from the Lerwick station. And the Camborne, and there's another one at Lancaster, didn't have such a big increase. This is kind of what we would expect with, as I was saying earlier, that the higher latitude sites typically have an increase in radiation. So by having the three different measurements, so having the space-based from satellite, air from the radiosondes, and ground from the neutron monitors, we're able to get this view sort of throughout the atmosphere of what's happening in a radiation event. And why this is important is, like previously when we've been trying to warn on radiation, it's been tricky to know if you're actually seeing much of an increase in ground level. This was sort of evidenced in January when we had a fairly significant radiation storm at satellite orbits that didn't translate down to the Earth's surface. So we saw this increase in lower energy particles at satellite level, which is kind of what we warn on, because that's the capability that we've had up until now. But as you can kind of see, the bottom trace there is the neutron levels at Lerwick. And if anything, there's a drop. So there was the background levels and it dropped off. And this is actually fairly typical when we get geomagnetic storms. So this proves that heightened radiation at our satellite levels, which is where we previously had most of our monitoring, doesn't translate to ground level enhancements. So it's because of this that we're trying to sort of improve the modelling and monitoring capabilities that we've got at the Met Office. So whether this will be giving alerts when we experience ground level enhancements, or it feeds into models which can give an indication of radiation at aviation altitudes. We've also got new models which are giving impact-based assessments on what's happening through layers of the atmosphere during space weather events. So on the left-hand side there, there's outputs from a model which models the ionosphere and thermosphere. Thermospheric modelling is mostly impactful on satellite operations, but the ionosphere model will give us an indication of where you can expect impacts to GNSS, satellite communications, and HF comms as well. So as we're bringing all these new models, all this new capability into the Met Office, into MOSWOC, we're then trying to work out ways that we can best visualise this for different sectors, different customers. And we have a space weather severity forecast prototype, which I've also included there. And this is kind of the way that we're trying to move and evolve our forecast, developing new models and products with focus on impact-based forecasts. So this shows where we can expect the types of effects that would be impacting different users during a severe space weather event. So yeah, that was just a bit of a whistle-stop tour of space weather. So I will stop there and ask if you've got any questions.